One of the most puzzling phenomena are black holes. These extraordinary events in the universe are still a subject of intense analysis and fascination for theoretical astronomers and scientists. Similar to other astronomical objects, black holes are characterized by the immense size of their gravitational force. A complete lack of emitted light indicates a threshold beyond which physical science principles cease to function. First proposed by Albert Einstein in 1916 as part of his general theory of relativity, black holes remained merely speculative until modern technology made their observation possible in the 21st century. A turning point occurred in the 1960s, and scientists studying the Cygnus constellation accidentally discovered an unusual star with a brilliant blue body, one that emits a lot of X-ray radiation. This star is locked in orbit with an unidentified partner. Traditional explanations failed, till it was found to be entangled in the gravitational pull of a massive black hole, later named Cygnus X-1. The detection of Cygnus X-1 provided tangible evidence of the existence of black holes and commenced a transformational period in the study of these cosmic mysteries. Located about 6,000 light-years away from Earth, Cygnus X-1 possesses remarkable features. It has extraordinary density and generates a gravitational pull so potent that even photons cannot escape. This defining feature is what earned it the name black hole, successfully conveying the essence of these mysterious structures. Subsequent investigations have found an assortment of dispersed black holes throughout the universe, projections indicating that the Milky Way alone could contain more than 100 million. Despite the fact that their properties make direct observation difficult, numerous black holes have been identified by astronomers. Possible examples in our galaxy range from stellar mass black holes formed from the collapsed cores of massive stars to enormous black holes at the center of galaxies. The gravity exerted by black holes affects not only their immediate surroundings, but also the broader growth of universal structures. Matter that comes too close to a black hole meets a grim fate. Possessing an unrelenting gravitational force, the black hole gradually drags matter toward its event horizon, the final barrier where it experiences extreme stretching due to gravity and is eventually absorbed by the singularity. This dramatic process, known as spaghettification, occurs when an object gets close to the event horizon. The gravitational disparity between the parts of the object becomes so extreme that it elongates and deforms into a fine strand resembling spaghetti. The force of gravity overcomes the molecular bonds holding the object together, reducing it to a stream of particles that eventually merge with the singularity. Black holes offer a remarkable chance to study the extremes of the universe, yet they remain shrouded in mystery. Nature, through black holes, challenges our understanding of gravitational mechanics and space-time. In the vast backdrop of the cosmos, black holes act as cosmic guardians, inviting humankind to explore the uncharted and push the boundaries of understanding. Despite their distance, the nearest black hole being approximately 1,500 light-years away, concerns and questions persist. In 2021, scientists made a significant breakthrough by capturing the first definitive image of a black hole. Located at the center of galaxy M87, this remarkable achievement yielded pivotal information about black holes and their elusive nature. The image revealed that black holes are not just voids of absence, but complex structures. Through in-depth research and image analysis, scientists discerned three distinct layers within a black hole. 1. The event horizon, the outermost boundary beyond which nothing can return. Once crossed, gravitational acceleration becomes unstoppable. 2. The photon sphere, a region where light orbits the black hole endlessly. Any photon entering this area is trapped by gravitational forces. 3. The singularity, innermost core, where physical laws break down, plunging scientists into a realm of profound ambiguity and theoretical speculation. The variety and complexity of black holes pose significant challenges to scientific understanding. While many share this three-layer model, each black hole exhibits distinct behaviors that defy conventional classification. Consequently, Traditional scientific methods often fall short in investigating these cosmic giants, requiring novel approaches and creative thinking. Direct research is virtually impossible due to overwhelming gravitational constraints. Any instrument sent into a black hole would be destroyed. Thus, indirect observation remains the primary method for studying these objects. Despite numerous challenges, the pursuit of understanding continues. Many stellar hypotheses propose that black holes play crucial roles in cosmic evolution. Offering valuable insights into the nature of space and time, NASA's observations of the M87 black hole's central region revealed compelling signs of a supermassive black hole, confirming its massive influence. Despite countless obstacles, the human drive to explore and explain remains undeterred. In 1963, physicist Roy Kerr made a groundbreaking contribution by proposing a rotating black hole model. This shifted scientific paradigms and introduced the concept of the ergosphere region surrounding the black hole, where gravitational forces interact in such a way that total collapse is temporarily resisted. Inside this peculiar area, physics deviates dramatically, pointing to the intricate puzzles buried within black holes. Perhaps the most captivating outcome of Kerr's theory was the speculative concept of a wormhole, or Einstein-Rosen bridge. This idea proposes a tunnel-like connection between distant parts of the universe or even parallel realities. Wormholes emerge from the complex relationship between general relativity and space-time, envisioning reality as a four-dimensional tapestry. In this view, space-time is warped by mass, creating gravitational effects. Wormholes are theoretical shortcuts through this vast fabric, potentially linking distant locations in space and enabling rapid transit. Their journey across the universe, reliability, and usability of the structure continue to divide physicists. Whereas wormholes provide exciting possibilities for interstellar travel and experimentation in time, significant obstacles and theoretical inconsistencies temper these hopes. Their fragile nature challenges from quantum theory, and radiation raise questions about their function as a means of transportation. Additionally, general relativity creates restrictions on travel speeds, implying that even if wormholes exist, they were stable, they might prohibit travel faster than light. Faster than light travel remains a hallmark of science fiction. Despite this, wormholes continue to arouse scientific curiosity. Their idea, given shape by fundamental theorists, embodies the exciting concept of common passages and alternate dimensions, igniting the human imagination regarding the larger universe and its limitless potential. The desire to create a single, comprehensive explanation, one that fills the void left by the gravitational and quantum divide, has led scientists toward a theory of everything, comprehensive model that includes all forces and particles at the elementary level. A physicist who pioneered M theory heads the mission. Superstring theory has been improved by research. This theory represents a significant shift from conventional mental models by stating that the smallest units are not elementary particles. It's but tiny, vibrating strings like those used in musical instruments. These strings vibrate in distinct ways, generating the frequencies and forces that compose all known matter. According to this perspective, each particle represents a particular tone of these superstrings, made of fundamental elements, some of the most perplexing characteristics of black holes, exotic elements, and wormholes within Einstein's gravity equations may also be illuminated by this theory. The movement of strings through spacetime aids in the development of topological oddities and singularities. Superstring theory is beautiful, but extremely difficult, and calls for the existence of additional dimensions beyond the usual three spatial. In one temporal dimension, these unnoticed dimensions directly unobservable by humans, challenge our perception. Analogies from nature, such as fish living on a two-dimensional surface, demonstrate how beings with limited dimensional awareness may be unaware of higher spatial planes. It is believed that these hidden dimensions are compressed or curled. Despite being invisible in everyday life, they significantly influence physical phenomena. even though their exact nature is unknown. Their theoretical presence provides useful explanations for the universe's bizarre behavior. Additionally, the mathematical foundations of superstring theory have led to a revival in theoretical physics, showing connections between the intangible and the abstract. Indeed, the drive to find a theory of everything unites numerous fields of science, focusing on the deep relationship between natural numbers and physical laws. Despite this, superstring theory still awaits experimental support. Due to the invisibility of higher dimensions, its predictions are difficult to test. Therefore, the daring concept of superstring theory continues to captivate students and dreamers, encouraging humanity toward intellectual growth and a deeper understanding of the cosmos. As we move through the landscape of contemporary physics, we stand guided by this brilliant theory on the cusp of greater understanding and consciousness. Solving the quantum puzzle of black holes has long baffled researchers and continues to be one of the most profound challenges in physics. Despite countless attempts to solve this mystery with a complete solution, it remains elusive. Edward Witten, from the Institute for Advanced Study at Princeton, famously contributed to 21st century superstring theory. Though the theory emerged in the 20th century, it is relatively recent in its modern development. Recent events have rekindled hope. Independently, multiple teams have revealed significant progress, indicating that string theory may indeed provide a comprehensive solution. However, this progress is currently limited to simplified models in 2 dimensions, rather than the full 10-dimensional structure typically derived from string theory. Despite the significance of this advancement, a complete resolution remains pending due to the complexity of the issue. Presently, we face significant challenges. Pursuing a unified theory requires us to investigate the outermost regions of the universe, where a profound mismatch between reality and theory awaits. Revelation, the study of black holes, is essential to our understanding of the universe. It redefines fundamental assumptions about reality and encourages philosophical thought processes. Behind black holes and other astronomical phenomena like gamma ray bursts and neutron stars expose the intricate mechanisms that shape the cosmos. These energetic collisions and stellar events are more than just random occurrences. They serve as valuable indicators of cosmic behavior, illustrating how gravity and energy interact on scales far greater than humans once imagined. Black holes, once considered theoretical oddities, now play a crucial role in describing the dynamics of star formation, galaxies, and even the evolution of the universe itself. As scientific equipment advances, such as space-based telescopes and gravitational wave detectors, our ability to observe and investigate these enigmatic objects has improved. The discovery of gravitational waves caused by black hole mergers supports long-held expectations and has established a new frontier in astrophysical investigation. At the intersection of theory and observation is the ongoing effort to unify Einstein's general relativity with quantum mechanics. Black holes pose a unique problem. They embody singularities where both sets of rules must apply. Scientists are now compelled to reconsider the fundamentals of both disciplines. Like wormholes, black holes manipulate the fabric of space and time. They may hold the key to a future model that seamlessly incorporates gravity and quantum field theory. Till then, they remain both puzzles and promises, stimulating ongoing inquiry and sparking the imagination of a new generation. From string theory to Einstein to Hawking, from observers to theorists in astronomy, the narrative of black holes demonstrates the ever-evolving search for understanding our place in the universe. With each equation, simulation, and captured image, we not only get closer to unraveling the mysteries of these cosmic superpowers,